Hello, my name is Alex Chan from the University of Constance, and today I'll quickly do a brief video tutorial on the new paper/method called YOLO-Behaviour, a simple, flexible framework to automatically quantify new behaviors from videos. So in this short tutorial, I'll first go through how the whole thing works, how the pipeline works, what are the steps that you have to go through, and then a few points of whether this method is appropriate for your study system, because every study system is different and you really need to see if this is appropriate. And finally, run through the whole pipeline through the documentation from installation to running the sample code, hopefully to give you more information on how to actually run this thing. So YOLO stands for you only look once, and it's actually an object detector model. So what this means is that you put in an image and then the model reads in the image and outputs a bounding box in a class. So it tries to detect the objects. So for example, here it will be like laptop and then it draws a box around it, or chair and it draws a box around it. So it's also really famous for being really fast, really easy to use, and so on. So it's a really common model to detect things from an image. So this is YOLO in action. So these are some Siberian jays feeding on a feeding stick. So it's pretty well detected. The birds are really consistent. But this is not the behavior though. So in YOLO behavior, basically the idea is instead of drawing a box around the actual animal, like an object, we draw the box around a behavior. So in this case, I trained the model to detect the beak touching the fat or the beak pecking at the fat. Then instead of detecting objects, now we're detecting behaviors. And this is the whole idea of the YOLO behavior framework. So in the paper where you can read, I showcased this method in 5 different systems: the house sparrow visiting, provisioning videos, the Siberian jays eating, humans eating, and pigeons activity budget of a bunch of behaviors, and then giraffe zebras walking and browsing in Kenya. So hopefully all of these case studies can already give you an idea of what kind of situations this could work. So quickly on the pipeline, first you might have some annotated data from boars, for example. This is not needed, but is really good to have, especially for validation. Then from the boars data, what you could do is then sample some frames where the behavior of interest is happening, so that you can label them. And we really want to choose the frames where the behavior is happening, which might be rare or might be annoying to extract. So that's something to do. And then once these frames are extracted, you'll need to label them. So what that means is just drawing a box around the behavior. So for example, for the Siberian jay eating, I had to draw a bunch of boxes around the beak and the fat together. And then we can then train the model using this package called Ultralytics. Then after the model is trained, you can have a test video, do inference, which gives you bounding boxes and confidences. But then this is the first problem of the pipeline, because the output of the model is just boxes, right? So like as you can see here, it's boxes and confidence, which is the 0 point whatever number there. But this doesn't give you kind of like quantifiable behavior metrics. So these are just boxes during frames. So we need a way to link these detections together. And to do this, I use something called a tracking algorithm. So what a tracking algorithm does, classically, is to basically follow a box through a trajectory. So like these pigeons here walking around, what you would do is use a tracking algorithm to basically associate boxes in terms of temporal and spatial consistency. But here, instead of creating tracks of like the same pigeon, I create tracks of behavioral events. So imagine a bunch of eating detections at the same point, then it will associate that into an event. However, the thing about the tracking algorithm is that there are a lot of hyperparameters. So these are just some examples. There's the YOLO threshold and then different kind of time duration thresholds for the tracking algorithm to figure out which one to associate with. And to do this, to solve this, I had to run this grid search algorithm, which is basically a brute force thing of testing every combination and then choosing the best one. And after that, you have kind of the full pipeline where you can then take these optimal parameters and apply it into new videos. So I'll quickly go through a few criteria I wanted to talk about of like when this method would be appropriate. So while computer vision might seem magical, not every situation can use every solution. So there are different solutions for different study systems. So here are kind of like 4 criteria. So the most important one is whether the behavior is visually distinct from a single image. Second one is, do you have sufficient images to train the model? And do you have relatively consistent and not super noisy videos? And lastly, some data set to validate your results. So first, the first one. YOLO is a frame-wise model. What that means is it just takes in one image and outputs a prediction. So this is kind of the major thing to consider, because without temporal information, this method actually couldn't pick up certain behaviors that might require context before and after a frame. And for this, so the behavior of interest needs to be distinguishable from a single frame. So if you see an image, you as a human should be able to tell what behavior that is. And if you can, it's likely that the model can also do that. So I'll keep the behavior simple. And here's an example from the zebra giraffe dataset where here the running, trotting, and the walking is super similar within the frame. So if you input the video into some model, maybe it could tell. But from a single frame, because YOLO only treats a single frame, the walking, running, and trotting becomes confusing for the model. And another example is with the Siberian jays, which is actually something I tried but didn't work. So it's this submissive behavior. So these birds also do this submissive behavior where they flap their wings and then kind of like scream. And I tried using the framework to detect those, but then I found out it's really visually similar to just flying off. So like the birds fly in and out and also do this wing flap thing. But because YOLO only reads in frame by frame information, this behavior is then kind of harder to detect. So this is a really important thing to consider. The behavior of interest needs to be visually distinguishable. So something simple like head up, head down would work really well. So like an animal being head up or head down is super visually distinct. So the second point to consider is, do you have sufficient training data? So for this model, for all the case studies I showcased in the paper, I have around 1,000 to 1,500 frames overall. And if your behavior is really rare, so like if you have 5 videos and there's a behavior that only happened 5 times, then this method might be not the best. So back to the pipeline, actually a really important step is the sample frames part. So just from experience, labeling the frames, so like drawing the actual bounding boxes to create training data is actually really fast. So like drawing a box, dragging a box around a behavior actually doesn't take that long to annotate. I don't know, it takes like 2-3 seconds per frame. But an actual thing that might take a little longer time to prepare training data is to sample the correct frame. So sometimes I even need to manually go look for these events and then select certain frames that I want to label. So something to keep in mind, perhaps in terms of annotation effort, sampling frames might take longer. And then here is kind of a more general point. The third consideration is whether the videos are appropriate for computer vision. So what this means is, does the training data match the final use case? So you cannot expect the model to work by training it on indoor pigeons and expect it to work in outdoor pigeons just like that. So like usually you'll need training data that matches the final use case. And even better, you can just use, if you have an experimental setup of a certain kind, you can just use those frames to train your model. And then also just general kind of more common sense stuff is don't have super blurry videos or super distorted videos, and have it as clear as possible and stuff like that. And reduce occlusions as well. So if there's like a lot of animals occluding each other, then of course these algorithms won't work as well. So here's an example from the pigeon dataset. Oh, sorry. So this is a good example of the pigeon dataset. So the pigeons are more or less not super occluded, quite clear what they're doing, and stuff like that. And here's another example of just sparrows eating. So, for example, this would be a much more tricky situation than any algorithm because of how noisy and how occluded these sparrows are. And finally, the most important point is, another important point is, do you have a validation dataset ready? So with any new method on any new system, evaluation is super important. And a lot of times, visualizing the results can be misleading. So like sometimes it looks really good. While I think in terms of applying these models, visualizing the results is really important because most of the time if you look at the results, you can kind of feel how well the model is working. But also often it's can also be misleading. So make sure you have some numbers to back it up that the model is working correctly and is consistent. So for this, I would prepare some coded videos for accuracy measurement. So like if you have 5 or 10 test videos, you can use Boris to kind of code the rates and then to make sure that what you get from the model automatically matches what you have manually. Yeah, and that's it. So now I'll move on to kind of more practical tutorial on how to run everything. Okay, now we'll quickly kind of run through basically all the code in a visual format instead of reading the documentation, and kind of just run through the basic functionalities of the whole code base and for you to be able to reproduce this for your own study system. So this is the main GitHub repository for the project. If you have GitHub on your computer, you could just clone this using this link. Or if you don't have GitHub, it's fine. You can just download the code base using this zip. And if you scroll down, you can then open the documentation. This is where I wrote detailed documentation on every step of the pipeline so that you can use it on your own. But in this video, basically, I'll also go through everything to a basic understanding of what each step does and what you have to do. So here in the first page, I also go through what I just went through with the 4 criteria of when you should choose this method. And to start, you should go to the introduction and installation page, and then make sure you download the repository, just what I said just now. And here, for example, I have it here, YOLO-Behaviour repo, and all the code and images are here. Then the next thing you have to do is also download or clone the sort repository. So here I could just download zip, and then I should extract it within the YOLO-Behaviour repository. I should make a new folder called repositories, and then put it there. Now it's there. I think I need to remove the master. So it's just sort sitting in the repositories folder. And then the next thing is downloading the example dataset. So here's an Edwin data repository on the sample data. So in the same as the repository, the sort repository. You'll have to download it and then put it under the data folder. So before I recorded this, I already downloaded it because it takes a little while to download. So next, we can start installing everything required. So first, I would recommend installing something called Anaconda, which is a super most well-known and used package manager to kind of install Python packages. So you can follow this link to just download now, and then whatever system you're using, you can download the appropriate version. And then after installing, so I already have it installed on my computer, you can just open an Anaconda prompt, which now goes to a terminal. But don't be scared. This is just, you'll have to start typing some code to move around. So the most important one is called CD, which stands for change directory. So you want to change and move to the directory you want. So I would CD documents, like to go to my, basically where I saved the code. You can press tab to autocomplete. So now I'm inside the YOLO-Behaviour repository. And then all we need to do is to kind of copy and paste these things. We create a repository called YOLO, not repository, create an environment called YOLO. So it will ask you if it wants to install all this. So just do Y, standing for yes. Yep, so now the environment is created, and then to launch it, to activate this, you have to type conda activate YOLO. So now you just look at the left here, it's now under the YOLO environment. So every time you run some code and you want to use the appropriate packages that you installed for this project, you'll have to type conda activate YOLO. And then you can also, if you want to change, you can do conda deactivate, which goes back to base. So it's just kind of an environment where all the packages are installed, and then you need to activate to kind of access those. Then next, you can pip install. This just installs all the packages required, which I put into the requirement.txt. There. So now everything's installed and we're ready to go. Yeah, so as I said earlier, basically every time you run the code now, you need to first run conda activate YOLO to kind of activate this environment. So overall, we'll now quickly go through all the scripts needed to run the pipeline, and also kind of quickly show you the sample dataset. So here we have all the weights from the manuscript, and then also YOLO datasets for 4 out of 5 of the case studies, and also I provided J sample data. So here I provided just a 5-minute short snippet of J's feeding so that we can run through the sample script together. So let's move on. So the first step is image annotation. So to train this YOLO model, we basically need a bunch of images where you drew the ground truth box on images to be able to, for the models to learn the behavior. And there are a lot of annotation tools out there. You can use whatever you want because the YOLO Ultralytics format is quite standardized. A lot of software could output that format. But here, basically, I will talk you through using an open source tool called Label Studio. So a lot of annotation tools out there like RoboFlow or V7, whatever. What they do is you annotate on their website, and then they could basically, quote unquote, steal your data. So they own your data after you upload it. So I really like Label Studio because everything's local, and then you will not be scared of having your data being obtained by giant companies. So in this page, I basically walk through the whole pipeline for annotating data. So I could quickly go through it. So this is called Label Studio, and I also recommend installing it using Anaconda. So first, I'll actually recommend installing it as a separate environment so that it's just easier to keep different things separated. So if I do conda deactivate, and then I actually already have a environment called Label Studio, but I would basically do the same as what we did just now. So conda create -n Label Studio, and then this would create an environment called Label Studio, and then you can pip install Label Studio. It's that easy. For me, it should be already installed. Yep, everything's already satisfied. But for you, this will install. Then to launch it, just type label-studio, and it will launch it on kind of a local browser. And after you log in, here would be where all your annotation projects would be, and I will basically create a new one. Let's say JSample. And then the data import, you can basically drag images into it. So I just prepared a quick J image as a sample, so you'll upload, I don't know, your hundreds or whatever, 1,000 images here. And then the labeling setup, it's really easy, just select the object detection with bounding boxes. So their sample is airplanes and cars, but let's say I want to do eat. So this is my behavior for the Cyber J's, and then I press save. So now I have this project called JSample, and I could press label all tasks. And the interface is quite simple. You can hold Control and then scroll to kind of zoom in and out. And then if you see the little 1 over here, if I press 1 on the keyboard, I could select and draw boxes as training data. And then you can click it, press here to delete. So for example, for this frame, what I would label is something like that. Then that's eat. Yeah, and then this guy is not eating actually. This guy is not, the beak is not touching the fat. Then after you're done with the frame, you just press submit, and then it will automatically go to the next image, but here, because I only have one image, it says no more task. So after you're done, what you have to do is to press export, and then export JSON min. So you can technically export whatever you want, but the sample script I provide uses the JSON min format. So now it's downloaded, and I've also provided a sample Label Studio data. So in the sample dataset folder that you should have downloaded under Label Studio, I have data and J annotations. So this is the JSON of the JSON min format. So this is all the annotations saved. And then here are the original images. So actually here is a tiny tricky thing that you have to do. So Label Studio does a weird thing where for the images, it will add kind of a unique code in front of it. And it's really makes it really hard to kind of look back for the images of the same name. So what you have to do is to look for where the images are stored. So usually what you do is, if you go back to where you launched Label Studio, you can scroll up. Where did I launch? Pip install, not here. Here. So here I typed Label Studio to launch it, right? So here they will basically tell you where they saved images. So for me, it's users, my name, app data, local, Label Studio, Label Studio. Yeah, so basically what you have to do is to go to that folder. This PC, see users, Alex, and it's app data. Beware, these are usually hidden folders. And then Label Studio, Label Studio, Label Studio, and then media, upload, and then 1 and 2. So usually in your project, you'll be able to see this is under upload 2, and then the code of the image. So here, basically, I would need folder 2, which was the image I annotated as a sample. So this is something you have to do because the image names are all changed. So ideally you can copy this somewhere in your computer. Okay, and then now basically we can try run some code. So after doing some annotations, this I already showed you, we can export the dataset. So we need the annotations as a JSON min, and then you need to get the images. Also what I already showed, and you can then run this code to to convert the format into the correct format for YOLO. So I would recommend downloading some kind of IDE to kind of access the code, like VS Code or PyCharm or whatever you prefer. If you're using VS Code, make sure you download the Python extension before you start. So once you're here, down here you can press the interpreter here. So usually it says Python. So you have to click it and then select YOLO, which is the environment we're using. And then after that, we can just run it actually. So for the sample dataset, I have the data under Label Studio specified here. The annotations are under JSON. And then it will output it into YOLO dataset. So I could literally just press this and it runs. And now it's done. So now you have the dataset ready, basically. So this is kind of the YOLO image and label format that you can use for them to train the model. So now the training data is ready. So you can then move on to model training. So before going to model training, it's a super quick point on GPU access. So GPUs are basically, the long-term form is called graphical processing units, which is usually designed for video games. But since AI and machine learning exploded, basically all of these models require good GPU to run. So you don't need one, but having one speeds up everything like 10 times. So just running these models on your CPU is really, really, really slow. So if you're planning to kind of deploy this model into like a lot of videos, thousands of videos, a lot of hours, then I would recommend getting a good GPU. So something like a gaming laptop or a gaming PC would work perfectly. So usually they have a really good GPU. Or good thing to consider is a lot of universities also have these large GPUs that you could use, or worst case, you can also use something like Google Colab where you can pay a little bit of money to get good GPUs for model training. Just a quick advice is to ideally get a good NVIDIA GPU, because the packages are, it's easier to install stuff and make the code work with the GPU there. Yeah, so next is model training. So basically, to train a model, you need a config file for YOLO. So here I have an example config file under data, YOLO datasets, J's YOLO. So here, basically you need a path to your dataset and then just train and then validation. So and then down here, you need to specify the index and the class you have. So for the J's, it's only one eating class, but if you have more, you can type 1 and then whatever it is. Hello. And then up here for the path, I think ideally, usually the best is just to copy the whole absolute path. Just make sure it reads correctly. And then for training YOLO, it's just the second script. So you have to specify model type, which is, so N is for nano. You can do small, which is S, medium M, large L or X. So you can play around with all the models. So N is the smallest and the quickest one. And then the config file, and then how many epochs. So this is how long I should train for. If I run the script, oh, my relative paths are wrong. Okay, I'll just do this. Just do absolute pass for all. So this should work now. Alright, I'm dumb. Oh, I was dumb. I didn't write J2 here. J2. Now it should work. So yeah, so you have to make sure you specify the correct paths so that I could look for the images. Yep, so that worked. So now it will start training. So for training, what Ultralytics, which is the package we're using, does is, if you go to where you run the code, which is the YOLO-Behaviour repo, what they'll do is they'll create a runs folder. So inside runs, detect, there will be a new training run. I think the most updated is the train 4. So now this will start training. So you can see it's saving in train 4. So under train 4, you would see kind of the batch they're using. It's also really useful to kind of make sure the labels look good. So these are just the eating detection labels. They all seem to be fine. So if the labels or the converting scripts is buggy, you should check this one to make sure YOLO is reading the images correctly. So here, the training might take a long time depending on what computer or what GPU you have. But basically, after it's finished training, it will save the weights in the weights folder, and there will be a weight called the best weight or something. Then you just need to take that, and then it would work, hopefully. So here I'll just skip the training because it will take a while, but at the end you'll be able to see where your model stores the weights and then use that to run your inference. So here is to basically, now you have a model trained. So the most exciting thing then is to kind of, let's check the results. So here we can use the third script to kind of visualize, have a quick visualization of the results. So here we use the J sample, and then I've already copied the J best weight into the folder, which I provided here, back in the sample dataset, weights. So here are the weights I use for the manuscript. So here I'm just running that. So with this script, it will output a video output of basically what's going on. and the sample inference. There will be a frame. You can just enlarge it. There. So that's the eating detection. It's running a little bit slow because my GPU is not that good, but with a better GPU, it should be faster. Oh, let me press Q to stop it. So this also outputs a sample video in your current directory, so YOLO sample. So you can also look at it. So that's the, I only ran it for a few frames, but there it is. So this is just for a quick visualization. You can also run the same, but for number 4. So script number 4 also specify your video name and then where your weight is, so the jbest.pt, and then specify output pickle or CSV. So both could work. And then if you run this, it will run the model through the video. And then what would happen is it will save the results in the same directory as the video. And then you'll get, if you selected CSV, you'll get YOLO.csv. If you got pickle, it's just a pickle that only Python can read. So if you want to do some further data manipulation, you can select CSV, and then you can basically get all the detections here. So here's the frame number, the behavior that was detected, the confidence, and the bounding box min, xy, xy, xmin, ymin, xmax, ymax. What this means is xmin, ymin is like the top left corner of the bounding box, and then the xmax, ymax is the bottom corner of the bounding box. So with these 4 numbers, you can draw the box and then the confidence. So after you ran the inference, basically you can select CSV or pickle, as I just said, and then basically CSV is much nicer for you to be able to look at the data yourself, but I generally also like pickle because it's just everything's within Python and I can just read it directly. But if you look at the data again, these are just detections, right? So we need to connect these detections together to become behavioral events. And to do that, we need some hyperparameters. So as I said in the first kind of presentation, introduction, there's a bunch of hyperparameters you have to tune. So in the manuscript, I basically found these were the best for the J's. So I'll talk about the grid search later to like how do we find the best parameters. But basically you can specify this into a JSON or a dictionary. If you press number 5 to get events, so this associates detections together. We stop that. Yeah, so you can also just specify it as a dictionary. So for eat, these are the parameters. So I would first load the pickle, and then this would associate the events, associate the detections and output events. No such file. Hyperparameters. I changed the name for some reason. Yeah, so this is just processing eat. And then this, with the done, it would output the output events.csv. Then now you have eating, start, end, frame number, and then these are all the tallies of when these events happened. Then that's it. Then you can basically use this for analysis if then this is the final thing. Yeah, but of course, validation is important, so we don't know if it's good yet, and then these hyperparameters need to be tuned to make sure it's good if you're applying this to a new system. Okay, now I'll move on to validation and grid search. So this part is, I guess, the step that requires the most customization, because every dataset is different. You're getting different kinds of data, you're quantifying different events, stuff like that. So this would differ case by case. So here I still show an example for the Siberian jays eating, but for your own system, you'll unfortunately have to write your own code for this one. So basically, the idea is you want validation, or you want some metric to show how good the method is, so like how accurate it is. And to do that, you can check out the manuscript, but we quantify a few scores. So one is called precision, one is called recall. Precision being how, for all the events that YOLO detected, how much of them were correct. So like how accurate in general the model is. And then recall is out of all the ground truth, how much the model recalled. So how much out of the ground truth it detected. And if you combine those two together, there's a metric called F1 score, which tries to balance both of them. And to get these metrics, basically, the most important thing is you want to kind of collate two lists. You want to build up two lists. So these lists can be frame by frame. So for the pigeons and the caber dataset in the manuscript, each entry in this list is one frame. So like in this frame, YOLO thought it's eating, and then the ground truth says it's eating. So it's eat and eat, for example. But in the J case, each entry here is a time window. So like a short time window. So basically out of the whole data stream, I cut it into windows, and then for each window, if there's eating in both, I count it as correct. So it's 1 and 1, and then maybe 0 and 1 if it's not correct. So the idea of this is you want to write up a whole code with your annotated data set to collate the ground truth and the predicted data. So you can go back to the inference to get this inference CSV, and then you can basically, like, not inference CSV, the events CSV, and then you can try to match these events up with your ground truth labels. So I won't go through in detail the code, but basically once you have the ground truth data and the predicted data as a list, so it's here, so I just turned them to strings. Basically here I used a bunch of just pre-available functions to calculate these metrics. So this plots a confusion matrix, and then here the classification report prints out all the metrics. So I could run it quickly. So number 6, sample validation. So I just use these Boris annotations I use as a ground truth. Okay, so it took a while to run, but now it's finished, and this is the output confusion matrix. If you press Q to close it, these are the metrics. So the precision for pecking 0.94, recall 9.5, and the F1 score. It also gives an accuracy 0.91, also calculated separately. But then here are the metrics that you can look at for your different behaviors and then figure out if it's good. And then once you write this sample validation script, you can really easily change it, adopt it put it into the grid search algorithm. So like looking for the best parameters. So here is an example. It's basically the same script with the difference of the starting part. So here I defined a dictionary of all the different values to explore. And then it's an expand grid function that changes this into a data frame. So it's a brute force algorithm that we try every single combination. So this will take a while to run. So I provide example to loop it, or you can uncomment this to basically do it in parallel. So this is the first difference. You have to the validation function you write should read in, so this grid search function or the validation function should read in the behavioral parameter and then have some output. And the output should be basically the precision, recall, F1 score, and support. And this you can get from this other function. So it's literally just these saved appropriately into the dictionary and then including iteration, outputted, and saved. Then after this, you'll have a data frame of all of the combinations and the results, and then you can basically print the max index, and then these would be the best parameters. So this, of course, would take a while to run because it runs through a lot of combinations. So you can also, I would recommend doing some manual exploration first to see what range of parameters you want to explore and then explore it. I would also say if this step is not strictly required, so if you're already happy with the initial parameters you choose, so for example 0.94 is already good enough for you, then maybe it's also okay. And then finally, the last kind of sample code I provide is the human in the loop method. So here's the idea of if the results of the model is not satisfactory enough and you want to basically manually review it. I also provide a script where you can read in the video, the detection file, and then it lets you do manual review. So you can literally just press yes to accept and then no to reject. So it's just a sample script. Again, you can modify this as you like. Here's the script, and then you can also you can modify it or change it so that it's not yes, no. You can do it 1, 2, 3, 4 for different behaviors. So it's just here. So now this is Y or N for yes and no. So if I run this on the sample data set, it needs to first write videos. There, so after writing the videos, there'll be a screen, and then yes to approve, yes, or N to disapprove. So this eat is correct. So I press Y. Then there's another case, press Y. Yes, 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 and so on. So this one, yep. So basically this kind of replays each detected event and lets you review it. So there's also a yes, 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 and so on and so forth. Basically after going through all of them, the results should be saved in somewhere. So it will save in video chunks, and then there's a tracks info. So in this CSV, you can see the previous event CSV and then the manual review true or false. So they are just put all true, but then technically you can then use this script as a base, so you can extend it as you like for your own applications to basically manual review that all these events are correct. Then that's it. That's the whole pipeline. So after this, you can again just use true or false to filter out the incorrect events and then use this for later analysis. So overall, this tutorial just kind of go through the sample scripts, but of course for actual use, I recommend applying these scripts, copying the scripts to your own directories, and then rewrite it so that it could loop through your videos or whatever data structure you have. So really, it might be Python, and if you're not familiar with Python, it's not too bad. Don't be too scared. And it can also output into CSVs and any later analysis you can do with other programming software. But just as hopefully this tutorial is useful. But if you want more details, everything I've talked about or gone through is also in this documentation page. So feel free to check it out, try it out in your own system, and if you have any questions, feel free to email me as well. Here. Cool. Thanks, and good luck.